Ever wondered about the strange world of quantum physics where reality takes a back seat? Welcome to the realm where particles can exist in two places at once, where they can pass through impenetrable barriers, and where they can be entangled over vast distances. It's a world that defies common sense and logic, but it's the world that forms the bedrock of modern physics and technology. Quantum physics, a field born in the early 20th century, has been puzzling and fascinating scientists for over 100 years. It's the theory that describes how the tiniest particles in the universe behave. And it's not just a playground for theoretical physicists. The principles of quantum physics are at the heart of the devices we use every day, from the silicon chips in your smartphone to the lasers in your Blu-ray players. Prepare to leave your everyday understanding of reality at the door. We're about to embark on a journey into the quantum realm, where the impossible becomes possible, where the certainties of classical physics fall away, and where the very fabric of reality is woven from uncertainty and probability. Dive into the uncanny world of quantum physics with us. Did you know light can behave both as a particle and a wave? This fascinating concept, known as wave-particle duality, is a cornerstone of quantum physics. It's a bit like how an actor can play multiple roles in a play. Light can play the role of both a particle and a wave. Let's take a step back and consider the world around us. We see that light behaves like particles when it interacts with matter. For example, when sunlight strikes a leaf and is absorbed, driving photosynthesis. On the other hand, light behaves like waves when it propagates through space, just like ripples spreading across a pond after you throw a stone in it. But here is where things get really strange. The famous double-slit experiment demonstrates this odd behavior. When light is shone through two slits onto a screen, we observe an interference pattern as if light was a wave. But if we try to observe which slit the light goes through, we see it behaving as particles. It's as if the act of observing decides the role light is going to play. This is not just some peculiar property of light, but all quantum particles share this duality. They can be particles or waves, and sometimes both at the same time. It's one of the great mysteries of quantum physics and shows us just how bizarre and wonderful our universe truly is. Yes, light can be both a particle and a wave, depending on how you observe it. Ever heard of Schrödinger's cat being both dead and alive? This peculiar idea can be attributed to a fundamental concept in quantum physics known as superposition. It's a bit of a mind-bender, so let's break it down. In the everyday world, an object exists in one state at a time. Your coffee can be hot or cold, but it can't be both simultaneously. In the quantum realm, however, things don't play by these rules. Just like Schrödinger's hypothetical cat, which is both alive and dead until someone opens the box to check, particles can exist in multiple states at once. This is superposition. A quantum particle, say an electron, doesn't commit to a definite state until it's measured or observed. Until then, it exists in a sort of fuzzy state of all possible outcomes. Now you might be wondering, how can something be in multiple states at the same time? Well, the secret lies in the wave-like nature of quantum particles. These waves represent probabilities, and it's only when you measure a particle that these waves collapse into a single definite state. So in essence, superposition allows particles to be in several states simultaneously until observed. It's as if they're in all the places they could possibly be all at once. It's a concept that defies our everyday logic, but it's one of the many reasons why quantum physics is so fascinating. In the quantum world, things can be in multiple places at the same time. Can you measure the speed and position of a particle at the same time? This question brings us to the crux of Heisenberg's uncertainty principle. It's a fundamental concept in quantum physics that tells us something rather counterintuitive. Ready for it? Here it is. You cannot precisely measure both the position and the momentum of a particle at the same time. Let's break it down a bit. In everyday life, if you're playing cricket, you can easily measure the speed of the ball and know its location at the same time. But when we go down to the atomic and subatomic level, things get a little fuzzy. Heisenberg's uncertainty principle states that the more accurately we know the position of a tiny particle, like an electron, the less accurately we can know about its momentum, and vice versa. It's not because of any limitations in our measurement tools or techniques, but rather a fundamental aspect of nature itself. You might be wondering why this is so. Well, it's largely due to the wave-like nature of particles. When we're trying to pin down a particle's location, we're effectively trying to squeeze a wave into a smaller space. This makes the wave spread out in momentum space, making the momentum less certain. This principle has profound implications on the nature of reality. It tells us that at the smallest scales, nature is inherently fuzzy and uncertain. So the next time you're trying to find out where you left your keys and how fast they're moving, remember, in quantum physics, the more accurately you know one quantity, the less accurately you can know the other. Can a particle pass through an impenetrable barrier? This question might sound absurd if asked in the realm of classical physics, but when it comes to quantum physics, the answer is a resounding yes. Welcome to the fascinating world of quantum tunneling, a phenomenon that allows particles to pass through barriers that should be, by all classical logic, impenetrable. Think of it like this. You're walking into a wall. According to the laws of classical physics, you'd bump your nose. But in a quantum world, there's a minute chance you could pass right through it. Now don't get too excited. This doesn't mean we can start walking through walls. Quantum tunneling occurs on an incredibly small scale and works with particles like electrons. It's a fundamental principle in quantum mechanics, where particles can exist in multiple places at once and can tunnel through barriers as if they weren't even there. This might sound like science fiction, but it's actually at the heart of many real-world applications. Ever heard of a scanning tunneling microscope? It uses the principle of quantum tunneling to image surfaces at the atomic level. Or how about the sun? Quantum tunneling plays a critical role in nuclear fusion, the process that powers our sun and stars. Quantum tunneling is a great example of how quantum physics challenges and expands our understanding of the universe, breaking down barriers, both metaphorical and literal. So the next time you find yourself facing an obstacle, just remember, quantum tunneling defies the conventional understanding of barriers. Can two particles be interconnected, no matter the distance between them? Let's dive into the mind-bending world of quantum entanglement, a phenomenon that has left even the brightest of minds in awe. Imagine you have a pair of dice. You roll them on opposite sides of a room, and despite the distance between them, they always land on the same number. This is a rough analogy for quantum entanglement. In the quantum realm, two particles can become entangled, meaning their states are interlinked. The fascinating part is, once these particles are entangled, a change to one particle instantly affects the other, no matter how far apart they are. It's as if these particles are communicating faster than the speed of light. But don't let this trick you into thinking it defies Einstein's theory of relativity. While it seems instantaneous, there's no actual transfer of information. It's just the spooky correlation between the two particles. This phenomenon has been experimentally confirmed, leading to mind-blowing technologies like quantum computing and potentially even quantum teleportation. It's a concept so strange that even Einstein himself referred to it as spooky action at a distance. So what does this all mean for us? Quantum entanglement paints a picture of a universe that is deeply interconnected, far beyond our everyday experience and understanding. It's a reminder of how wonderfully strange our universe really is. Quantum entanglement shows us that the universe is deeply interconnected. Is teleportation only a science fiction concept? Not quite. Welcome to the realm of quantum teleportation. Now, before you get too excited, we're not talking about teleporting humans or physical objects. Rather, quantum teleportation is about the instant transfer of information about a particle's state to another particle, irrespective of the distance between them. Let's unpack this. In the quantum world, particles can be entangled, a strange phenomenon where two particles become interconnected. When this happens, the state of one particle immediately influences the other, no matter how far apart they are. It's like two entangled particles are singing the same song in perfect harmony across the vastness of space. Now, quantum teleportation leverages this entanglement. When we measure the state of a particle, that information can be instantly teleported to its entangled partner. This transfer of information happens faster than light, defying Einstein's relativity. But don't worry, it doesn't violate any laws of physics. It's just that quantum mechanics plays by its own, rather quirky set of rules. To be clear, quantum teleportation doesn't transport the particle itself, only the information about its state. So while it's not quite the beam me up Scotty of Star Trek fame, it's still pretty mind-boggling and hints at the unimaginable possibilities of the quantum world. Quantum teleportation, though not yet possible for humans, is a reality for particles. Can computers use quantum physics for super-fast calculations? Well, that's precisely the question that led to the concept of quantum computing. Imagine a system that could process information at a speed that's almost unfathomable, a system that can solve complex problems in a fraction of the time it takes even the most powerful traditional computers. This is the potential of quantum computing. In a classical computer, information is stored in bits. Each bit can be a 0 or a 1, the binary language that underpins all digital systems. But quantum computing, on the other hand, uses quantum bits, or qubits. These aren't limited to being just a 0 or a 1. Thanks to a phenomenon known as superposition, a qubit can be both at the same time. But that's not all. Qubits can also be entangled, a unique quantum property where the state of one qubit immediately influences the state of another, no matter the distance between them. This means quantum computers can perform many calculations simultaneously, making them incredibly powerful and fast. Quantum computing is still in its early stages, but the possibilities are extraordinary. From revolutionizing encryption and cybersecurity to accelerating breakthroughs in artificial intelligence and material science, quantum computing could fundamentally change how we understand and interact with the digital world. However, it's not without challenges. Creating and maintaining a stable quantum state is incredibly complex, and errors can easily creep into calculations. But as scientists and engineers continue to push the boundaries of quantum technology, we inch closer to realizing its full potential. Quantum computing could revolutionize technology as we know it. The quantum realm is a strange and fascinating place, and it's one that we're just beginning to explore. Can quantum physics and gravity be reconciled? This is a question that has puzzled some of the greatest minds in physics for nearly a century. You see, quantum physics and gravity have always been at odds. Quantum physics, with its focus on the minute world of particles, operates on a different set of rules than gravity, which deals with massive objects and the fabric of space-time. These two theories are like two distinct languages, each perfectly describing their own realms but unable to communicate with each other. Physicists have long sought a unified theory, a quantum theory of gravity, that would bridge this gap. This theoretical framework, often referred to as quantum gravity, would reconcile the small-scale world of quantum mechanics with the large-scale world of general relativity. One promising candidate for this unified theory is string theory, which proposes that all fundamental particles are tiny, vibrating strings. Another is loop quantum gravity, a theory that quantizes space-time itself. Yet, despite the progress made, a complete theory of quantum gravity remains elusive. Scientists have yet to find a way to fully marry the principles of quantum mechanics with those of gravity in a way that's supported by experimental evidence. But this doesn't mean they've given up. Far from it. Physicists continue to push the boundaries of our understanding, delving deeper into the mysteries of the universe. The quest for a theory of quantum gravity remains one of the biggest challenges in physics. How does quantum physics shape our understanding of the universe? Let's dive in. Quantum physics, the science of the very small, has an unanticipated influence on the grandest scales imaginable. It's the key to understanding the nature of reality, from the tiniest particles to the vastness of the cosmos. Take black holes, for instance. These cosmic behemoths, the remnants of collapsed stars, are where quantum physics and gravity collide. Inside a black hole, space and time warp, and the laws of physics as we know them cease to apply. But quantum physics offers a lifeline with the concept of Hawking radiation, a theoretical prediction by physicist Stephen Hawking. According to this theory, black holes aren't entirely black, but emit tiny amounts of thermal radiation due to quantum effects near the event horizon. And then there's the Big Bang, the event that kick-started the universe as we know it. Quantum physics suggests that before the Big Bang, the universe was a singularity, a point of infinite density. This idea challenges our understanding of space and time, offering a radically different picture of the universe's origins. Quantum physics even contributes to the cosmic inflation theory, suggesting the universe expanded exponentially in the first split second after the Big Bang. This theory helps explain why the universe appears flat and uniform in all directions. And let's not forget the fascinating concept of virtual particles. These ephemeral entities pop in and out of existence in empty space, a phenomenon permitted by the uncertainty principle of quantum mechanics. So, you see, from black holes to the Big Bang, quantum physics is intrinsically woven into the fabric of our universe, helping us decipher its mysteries. Quantum physics continues to reshape our understanding of the universe. Quantum physics, isn't it a fascinating field? We've journeyed through the intriguing depths of wave-particle duality, where light and particles have dual properties. We've explored the bewildering concept of quantum superposition, where particles can exist in multiple states simultaneously. We've grappled with Heisenberg's uncertainty principle and the inherent unpredictability it introduces to the quantum realm. We've delved into the miraculous phenomenon of quantum tunneling and quantum entanglement, shattering our conventional understandings of space and time. We've also been mystified by quantum teleportation and its potential implications for the future of communication. Quantum computing, another topic we've touched upon, promises to revolutionize our technological landscape. We've pondered over the elusive theory of quantum gravity, a field still ripe with unanswered questions. Finally, we've looked at how quantum physics shapes our universe, from the smallest particles to the grandest cosmological structures. As we wrap up our journey, let's remember that these 10 fascinating facts are just the tip of the iceberg. There's so much more to uncover as the quantum world is teeming with enigmas waiting to be solved. So stay curious and keep exploring the fascinating world of quantum physics.